Thank you.
Okay. Just give me 1 sec. All right, so the title of our project is DataScope, Predictive Diagnosis and Internet of Things Enables Smart Manufacturing. And this is a collaborative project between Elizabethtown College, CPNet LLC, and with business domain advising from HPI Resources. And the problem itself is coming from CPNet.
So first, I'm just going to talk everyone through our agenda just to let you know what we're going to go over in this presentation. In our introduction, we're just going to briefly explain our problem and how we want to solve it using predictive maintenance. In motivations, we're going to talk about the motivations behind our research. That one's pretty self-explanatory. In design, we're going to explain our data pipeline and the process we use to make our machine learning work for us here. In evaluation, we're going to look at our results from our machine learning, and in the conclusions, we're going to assess the value we added to the domain by doing this project and what further research needs to be done on the subject.
Right, so for introduction, our big problem is being able to predict when a machine is going to fail and to notify our operators. Now, the machines that we're working on are from CPNet's client. It's a manufacturing facility. So originally our plan was to take the data set that we acquired from CPNet and some of their code and create an alert system that would be able to predict when the machine is going to fail based on some certain part dimensions and limiting thresholds for operations of those part dimensions. And then, yeah, basically create an alert system that would notify the operators at the facility if something seems like it's going to fail in the future. But after the first few weeks, we decided that this project might be a little too ambitious for a 10-week project. So, and especially for 2 beginner data science students. So we decided to just narrow our scope down to focusing on the predictive maintenance portion of this problem. Some existing solutions consist of SPC analysis, which is statistical process control analysis. And it's a type of analysis where you perform quality control using statistical methods to monitor a process. And in this case, the process would be monitoring the part dimensions of the machines we're looking at. And we're looking at, building and improving upon the ideas of SPC and bringing them into predictive maintenance. So predictive maintenance is how we're going to go about solving our problem. And it's a way of using data analysis to detect anomalies or variations in a process or equipment in the hopes that you'll be able to fix problems before it results in a failure of the system or the equipment. And right now the machines are being run to failure. And then after it fails, corrective maintenance is performed, which takes time and money, since when the machine fails, it's not always apparent what caused the failure. So not only is the machine down, but it also takes time to diagnose what happened, how to fix it. And then while it's down, they're not making money from the products that are being produced. And then also it costs money to replace any broken parts. So continuation on that slide, we have 2 problems from the data itself, which is that first off, the time series data lacks run to failure indicators, making physical modeling nearly impossible. And then also we don't have any data labels for a regression analysis. So we're going to need to combat that by creating our own data labels further on down the line. So our unique solution to solving this problem is remaining useful life, RUL for short. And basically in a nutshell, RUL is an estimate of the remaining time a machine, component, or system has that it can operate before it's likely to fail or need some kind of maintenance and takes it down. But in order to perform predictive maintenance, we're going to need data labels. And the data labels that we're going to use is the health index, which is basically, the health index is like an assessment of how healthy your machine is at any given point. So with that, like I said, at any given point, you're able to tell how healthy the machine is from, like, say, a scale of 100% being completely healthy down to 0%, which would be completely complete failure. But in order to create the health index, we need to use CPK analysis and PCA analysis to generate our Y labels.
So this graph here works as a great example of RUL and the health index. So what we have is the health index on the Y here, and that goes from 1 to 0, 1 being perfectly healthy and 0 basically being completely destroyed or complete failure, as Adam said. So our blue lines represent previous iterations of whatever machine this graph was based on. Could be some sort of machine or a part in some process. And we have their failure marks. When that machine failed, it's marked by that dark blue star down there. And the red line is indicating current data, a machine that's in the middle of its lifespan. And so we would expect that to fail somewhere around the 0.3 mark on our y-axis here, or maybe 200 cycles on the x, just based on what we've seen in the past. And that's basically what we're doing with RUL. If we can get the next slide. So this is just a basic overview of our data pipeline. So the first thing we have to do is fetch the data. Obviously, we can't do any work on it if we don't have up-to-date data. And specifically for this use case, this would be on a currently running process. So we would need to be bringing in data constantly so that we can be working on it in real time. In our specific data set, we only had a few columns that were particularly useful to us, and they were the tooling dimensions that were being tracked by the particular machine. Our next step would be to generate our Y label. As Adam mentioned earlier, there was no inherent Y in this data set, nothing for us to predict that already existed, so we had to generate our own. And what we did was use CPK analysis, which is a pretty standard industry practice that has been going on for a long time, and it basically measures how in control the process is and how likely you are to have parts coming out of the spec limits. And our final value, or our final step, is to just do the actual prediction. We need to plug the data into the actual model and get numbers out of it. So that's our entire thing, basically. Once we get to that point, we're just trying to get the future, we're trying to predict the future of our current machine and see if it's going to come out of control or if it's going to fail. And if we can get them, yeah, there we go. So I'm just going to go quickly over our models here, what we used and what they ended up looking like as far as our predictions went. So traditional machine learning models, you'll see here, are we tried all of these, and in general, the traditional machine learning models tended to be our best estimators. This was a relatively speaking short project, only 10 weeks, and a lot of that time we had to spend working on the data and generating the Y value. So we didn't have a whole lot of time to spend on the modeling. And so machine learning's easier ability to just plug and play was very helpful for us here, as opposed to neural networks, which you'll see down at the bottom, and we used all of those. And the thing with neural networks is, obviously, you have to build the architecture yourself. You have to design how that model is going to work, and there's parameters every step along the way that need to be tuned and tested and experimented with. And with our time frame, it really just wasn't going to work out for us to get those to be functioning perfectly, because there's no, since this project is basically treading new ground, no one has a previously devised model for this particular application. So we would have to come up with our own in order to do the work. That's all I have for this slide.
So in conclusion, as far as value added, we were able to identify and find a potential way to solve the predictive maintenance problem that we had. And while we didn't solve the problem that we initially set out to solve due to some time constraints and the complexity of the problem, we were able, like I said, to find some way that we can potentially solve the predictive maintenance problem through the use of remaining useful life and health index for that remaining useful life. And then also for further research, there's definitely potential to keep exploring this problem and solve it in subsequent research projects while we're at college. And hopefully we continue to do that. Or, say we graduate, maybe somebody else at the college can take up our research and continue working on this problem. And then just some general thoughts and opinions. Although it was a harder problem, and this is the first time we were working on some real world data science stuff, it was pretty rewarding. And I think both Reilly and I are really looking forward to potentially continuing with this problem and seeing it through to a potential solution or something, but continuing our research here. So, any questions?
So you can put questions in the chat or unmute and just ask.
Yeah, I had a quick question. Among the machine learning traditional algorithms you guys applied, did one method do better than the other, or they were all kind of similar in terms of predictive accuracy, or whichever metric you use?
Yeah, the traditional models seem to work better. We didn't have a lot of data, so the neural networks, they were fun to try, but they didn't work too well. Of the traditional models, the tree-based regression seemed to work the best, and followed by just the polynomial regression. But since we didn't completely get our health index to work like we wanted it to, we just kind of used what we had. So hopefully if we get the health index perfected, our model accuracy would go up a lot. But yeah, so the traditional models outperform the neural networks.
Another minute. We have another question. And if not, I'll say thank you to our speakers. Great presentation. And thank you for sharing with us today.
Thank you.
I have to find my little clapping reaction here. There we go. And then next up, so first in our program, but second today in the session, we have Matthew Grohotolski, and he'll be presenting for us on Sector, a web-based data management and sharing system secured by blockchain. And so you should be able to share your screen as needed there, Matthew, and you're ready to go.
All right, thank you very much. Give me one moment here. All right, should be sharing here.
Yeah,
we're seeing your presenter's view.
Oh, the presenter view. Let me switch it here. Oh, there we go. Okay. Yeah, I think I just selected the wrong thing. Hello, everyone. And today I'm presenting on my project Sector, and it's a web-based data management system. This is a joint project between Elizabethtown College and the University of Lowell, Massachusetts. And it is advised by Dr. Wang and Dr. Lee. So we have a table of contents here. First, we'll be starting off with why the implications of this project are important, a little bit of background on the project. We'll move into the motivation behind the project, and we'll cover some data management and how we use blockchain technology for the project. Then we'll cover how the file transfer system works and the background application that we use for that. And lastly, we'll go into the demonstration of the project with an overview of the website and the functionality of the transfers. And lastly, then we'll close off with a Q&A session at the end for any questions that you guys might have along the way. So why is this important? So 100% of organizations and institutions store some type of sensitive data already. And a vast majority of those organizations and institutions have some kind of need to transfer the secure data between universities or other companies. So that's where Sector comes in to fill that void and to give these institutions a way of transferring their data securely. So there's actually a limited amount of resources as well that currently exist to do this operation, and not many of them actually support the HIPAA standards
lost-
to transfer types of.
Yeah, we lost you for a
Oh.
moment.
Oh, sorry. Yeah, I think my connection went out for a second, but that's where Sector comes in to fill that void. We have a little bit of motivation here about the background of Sector. So some things that we wanted to achieve with this project is we wanted to utilize blockchain to store and serve all of the data that we collect securely. And we also wanted to create a new platform so that institutions and organizations have more options for how they can actually transfer their data and share it with other organizations. And lastly, of course, we wanted to abide by the HIPAA regulations so that Sector can provide some kind of peace of mind to their clients and provide accurate data protection for them. And now we'll be moving on to how we implemented blockchain. So on the left-hand side here, we can see the workflow and how that's set up. So we can see the client when they connect to the website, it gets connected to the Node.js system. And that is pretty much how the website is served to the user and has all of the functions for calling the Fabric API on the back end. And then from the Node.js website, it communicates directly with the Fabric, which is the blockchain network. So doing it this way with this workflow offers a great amount of customization. So pretty much anything that we need to store for data could be implemented. It's very easy to expand, and it's all the data stored on what's called a distributed ledger. So we actually just upgraded to a 6-server setup for this, for storing our data. And of those 6 servers, it's actually split in half. So one organization is, let's call it UMass Lowell. So that's comprised of the first 3 servers. And then another institution for University of Wisconsin is the second 3 servers. So by storing the data on this distributed ledger, if one organization has some kind of outage or malfunction, then the data is actually still accessible from the other organization. So this is a smarter means of having less downtime in case of outages for the website. And this Fabric or blockchain network is actually designed for HIPAA compliance. And like I said, that just delivers peace of mind for all the data that's stored, that it's secure. And next we'll move on to the Globus. So Globus is what we use to conduct the actual file transfers. So whereas Hyperledger Fabric is used to store like general user information or project information, Globus is how we actually get the file transfers from one endpoint to another. And I have a little bit of a workflow for that on the next slide, but some things that Globus offers is it's a secure data transfer platform. It has manageable fees associated with it. It is already HIPAA compliant, so all the data stays secure, but it does offer limited user control. So this is something that Sector aims to fix by giving a greater amount of control over the projects and all of the files. So you can actually go in and specify which users have access to which directories and files. And Yeah, so we'll move on to how we utilize Globus. So like I said, the Globus offers limited user control. So if you add a user to an endpoint, that user could then see all of the files associated with that endpoint. That's a real issue if you have some type of medical data or something and you have multiple research teams working on a given project. You want some way to be able to control this and say which users are allowed to access which certain contents of a project. So that's what this workflow kind of demonstrates here. I made this very early on in the project, and it demonstrates how we use multiple Globus endpoints to get around this restriction. So we have a user's personal endpoint. This is just how we interface with the user's computer to access their local files. And they would then upload to an upload endpoint. So this is where everybody has their own personal upload folders, and you only have access to your personal upload folder. And from there, the data is then transferred to the collection endpoint. And from here, this is where we can use our custom security system on the website to say what gets viewed on the user's screen. So this pretty much allows us to have finer granularity control over the different roles that the user has for the project. So if they're a researcher, they may have different access than if they were just a regular guest or a member. And now we'll move on to the demonstration for the website. So just have to change over the screen share. All right, so this is what the main website looks for Sector. So currently I'm signed in as a system administrator. You can see some different links here. So we have like get started and frequently asked questions. We'll go to the frequently asked questions just to show that. So this just has a list of normal questions generated by users that use Sector, and they've been answered here. So some of the things that we can do with Sector is we can go to the manage page, and this actually lists all of those Globus endpoints here. So right now I just have a collection set up. If we click into that, we can see some further details here. It has a Sector collection, and then we can actually see that upload collection I was talking about earlier listed here as well. So each endpoint has a collection endpoint and then also an upload. If we go to the projects tab, then we can see a project called eTown Test. It's under that Sector endpoint, and I currently have the role of owner on there. And that project path is just the normal directory of that endpoint. So we can see a little bit more information here, such as the name again. All the endpoints are listed here along with the directory, so you could make modifications to that. And then also all the users and the roles are listed under this project as well here. So we can see this account has owner access, but my personal account has just guest access to this project. It's very easy to also add users just by typing in an email address here. If they have a Globus account, then they're added to the project automatically. And they're also sent an email to notify them. So lastly here, then what I want to show off is the actual file transfers. So let me log out of this account here, and then I will log into my personal account that has that personal endpoint set up already. So now we can see I've successfully signed in as Matthew Grohotolski, my normal account here. And if I go to the transfer page, so this transfer page has your endpoints listed on the left-hand side. So in this example here, I'm just using my personal endpoint that is set up on this computer that I'm on currently. And I can actually navigate into these folders and do things such as like selecting them, or like going into the subfolders. So on the right-hand side here, we can see the project that I'm currently in is just eTown Test. So I'll select that and it'll load up the different folders and files associated with that. So if I go into my own personal folder here, we can see that there's a number of files here already. So let me try and actually rename one of these files here to transfer. So I will do scarp.txt. So now that scarp.txt file is just renamed, and I can actually conduct a real file transfer here. So some of the information that's required for transferring one of these files is like the file hash. So this is something the user can get to type in here. So for testing purposes, I'll just write the value test, and they'll select the project. So the project name isn't listed here just yet, but this should be eTown test. And then the group is guests. So I want guests to have access to this file. And since I'm a guest, it makes sense to select that option. And if I select, you can see the transfers processing here. And if I reload on the endpoint, we can see the scarp.txt file has been transferred successfully. So that would be how you transfer files through Sector. And all of the information from this is actually stored. So like the time that it was transferred and everything, so that the endpoint admin or the project admin can actually go in and see those stored files. But that is pretty much it for the website demonstration portion of this.
All right, thank you, Matt. Unfortunately, we're out of time, and we have 2 more presenters that we need to get in before the end of our session. So and we're going to have to wrap it up there.
Okay, sounds good.
Thank you. And so next up, we have, let's see, Aidan Hanley, and he will be sharing with us predicting the 2020 presidential election with multiple logistic regression.
It says I can't share my screen.
You should have permission.
I joined in a little later since I have the less recent version of Zoom. So I'm not sure.
Oh, and that may be why you can't share screen. Is
Yeah.
there, let's see, by any chance, Long, do you have a copy of the presentation that you can share?
I think
Because the only way
Cigar,
to fix that is to update your version of Zoom, as far as I know.
Oh,
Yeah.
okay.
Cigar, you can have the control.
Do you still have the recent version of our presentation?
Cigar, we can hear you. You're muted.
Sorry. Yeah, and why don't you email me your most recent if you
Yeah.
made any changes right away? Yeah, I'll share it.
Okay.
I have your fairly recent version, but I still
Yeah,
email
I'll
me.
send you the most recent.
Yeah.
Do we want to like go to the next person while we
Yeah,
do that?
maybe we should.
Okay.
And so, Colin, I believe you are up next. And so, Colin will be sharing with us on e-therapy, developing the next generation occupational therapy, physical therapy tool. And you're ready to go, Colin.
1 second. Okay. Before we begin, I'd like the audience to take a quick second to find the reactions tab at the bottom of your Zoom window, because I will soon be asking you a few questions that I'd like for you to respond to, which you can do by selecting the reactions tab. Thank you. But hi, everyone. My name is Colin Elliott, and with my faculty mentor, Dr. Kurt DeGood, at Elizabethtown College, we've created e-therapy, the next generation of physical and occupational therapy. To begin, I'd like to ask the audience a few questions. Please give a thumbs up for an answer of yes, or do nothing for an answer of no. Please give a thumbs up if you or someone you know has ever done physical or occupational therapy. Again, thumbs up for yes, do nothing for no. Okay, good. And for those who answered yes, please give a thumbs up if you or they found the recovery process challenging. Good, so a fairly large percentage of you would benefit from an improvement to the therapy process. Now let me give you a brief introduction to e-therapy. E-therapy is the application of wireless inertia sensors and software to create real-time awareness and tracking of therapeutic exercises. First, let me talk about the sensors. The inertia sensors have the ability to accurately identify their exact position in space. Hence, when configured around a person's joint, they can provide the precise range of motion of a joint, whether it be flexion extension, abduction adduction, rotation, etc. Now, in order to utilize this, I've created a mobile app that maps your body's real-time position in space directly onto your phone screen. If you view the GIF on the right side of the screen, you'll see a real-time capture of me using a single sensor attached to my chest, where I simply lean to the right and then lean forward and backward. There's much more to the functionality of the app, but first let's talk about how the sensors work. The inertia sensors contain 3 tools which work in unison to determine their exact location in space. First is a gyroscope. A gyroscope consists of a spinning axis, which is able to measure rotational velocity. Whenever the sensor rotates, a small mass in the gyroscope shifts position, and this shift in position is converted into an electric signal, which is proportional to the rotational velocity of the sensor. Keep in mind that the gyroscope only responds to rotation, so linear motion will have to be determined by another tool, and that is the accelerometer. Accelerometers measure linear acceleration by using piezoelectric materials, which convert mechanical stress into electrical signals. Hence, whenever the sensor undergoes a change in motion, this squeezes a piezoelectric material, which produces an electric charge proportional to the acceleration. This electric charge is then converted into a voltage, which is then measured. Accelerometers are everywhere and are most commonly seen in your smartphones. For example, whenever you turn your phone sideways, the screen knows to change the orientation of its display because of gravity's effect on the mass in the accelerometer. And last is a magnetometer. A magnetometer measures magnetic field intensity and direction, and is most commonly used in a compass. In the inertia sensors, it's used to determine the orientation of the sensor with respect to the Earth to know which direction the sensor is pointing in. Now let's talk about the software, which is what I'll spend my time creating this summer. Upon opening the app and surpassing the welcome screen, the user is prompted to log in. As you log in, you'll notice the app is designed independently for 2 distinct users, the therapist and the patient. First, we'll look at therapist mode. Upon logging in via therapist mode, you'll be directed to a screen with a bottom navigation menu with 3 menu options. The most important option for the therapist is the Patients tab, so we go there. As you can see, this tab features a list of your patients and a button allowing you to create patients. If you click to view an existing patient, you will see this screen, which contains the patient's name, the range of motion data, and the therapist assigned exercises for that patient. If you click the plus icon, you can create a new exercise for that patient, which appears as so. When creating an exercise, you'll name the exercise and then you'll select the joint on which to work on. In this case, that's the cervical spine. According to that selection, all possible range of motions of that joint will appear alongside switches, and the therapist can then select which range of motion will be part of the exercise. Notice that while the cervical spine has 3 ranges of motion, in comparison, the knee joint only has 1. And the ranges of motion have different names based on anatomical terminology. Scrolling down, we'll see the patient's range of motion data, which we receive via goniometer mode, and that's what the button is for, which is our tool for measuring the patient's maximum range of motion. This is what goniometer mode looks like, with my maximum range of motion data from my elbow shown towards the top of the screen. Next, the therapist will select targets for the patient, which are the range of motions that the patient will have to reach in their respective exercise. If you scroll down again, the therapist can designate the end condition for the exercise, whether it be time, repetitions, or until the patient says stop. Then it comes to the main functionality of therapist mode, and here's where the real action happens in patient mode. For uniformity, patient mode also contains a bottom navigation menu, both different menu options. On the to-do list tab, the patient can view scheduled exercises that the therapist assigned for them via a calendar widget. On the Me tab, you can view your own range of motion data. And finally, on the Activities tab, you can start your exercise activity. Upon clicking Therapy, you get a screen for connecting the sensors to your phone, and it works via Bluetooth. So first you must pair them, then you can connect to them. Once you connect to the sensors, an updated user interface will appear. Now you can do a couple of things with the sensors before you begin the activity. First, you can calibrate the sensors, which revitalizes their accuracy if they have seen repeated use over a long period of time. Next, you can change channels if there are multiple patients in the same room using the sensors. In order to control which sensors your phone connects to, you'll need to assign your sensors to the same channel. Fortunately, there are 26 different channels to choose from, so there should be no problem with distinguishing between sensors. Finally, you can select your exercise and begin. And you'll get a screen like this. Now, I know all of you want to see the process in action, so I'll show you a live demonstration of an elbow exercise, which contains flexion, rotation, and extension in that order. Okay, so now let's talk about the benefits of e-therapy. Compared to traditional physical and occupational therapy, e-therapy provides the ability to do therapy at your home or on the go. The therapist simply has to assign you an exercise, and you can ensure that it's done completely and correctly with e-therapy. For the first time, you can do therapy on your own and receive personalized feedback to see if you're more flexible today than yesterday. But there's no need to worry about self-assessment. Upon completing an exercise, a report will be sent directly to your therapist, where they can also assess your performance. While the software is currently geared towards therapy, the applications of the software are limitless. With these sensors, anybody with a passion for fitness can use e-therapy to take their fitness to another level. Say Larry wants to make sure he's squatting correctly. The e-therapy app will give an audio cue to Larry whenever his thighs are correctly oriented with the ground, so that Larry knows he's squatted down far enough. And it'll even notify Larry when he's done the planned number of reps for that day. With e-therapy, there's no more excuses for miscounting reps or for having improper form, which can lead to injury. E-therapy can help runners check their running form, gym goers perfect their lifting mechanics, and anybody check their own flexibility. The possibilities are exciting and endless. With e-therapy, we truly believe that the next generation of biometrics is here. In wrapping up this presentation, I'd like to thank the following for their support during this project. I'd like to thank the Elizabethtown College SCARP program for this amazing experience. I'd like to thank the Bowman Engineering Research Fund for providing funding for these projects. And finally, I'd like to thank the Knot Sensor Company for providing a baseline for software development. Any questions?
So there's a question there in the chat, Colin. How many body sensors can you connect to Bluetooth at one time? And I know there's a difference in that between with the real-time data versus non-real-time data.
Yeah, so it also depends on your phone in terms of your, so like if you have an Android compared to a iOS Apple phone, for example. So Android supports more devices total. I think the maximum for Android is 3 or 4, and the maximum for Apple is 3, I believe. But for each exercise, you only need 2 or 3, because if you were just doing, for example, like an elbow or knee exercise, you only need 2 sensors, one at each end of your joint. Now, if you're doing like a shoulder, it's more complicated because there's 3 ranges of motion, but you need 3. So regardless, your phone will always support how many sensors you need. Yeah.
And we have time for one more question if we have another.
Did you hit any roadblocks with your SCARP project?
Yeah, so initially I had to learn how to obviously like use Android software development kit and like learn how to code in Android. Now the language is like Java, so I learned that in Computer Science 1, but all the functionality in terms of like displaying everything to the screen and like doing all the cool things in the actual app was learning how Android. And also that was one major roadblock. And the second major roadblock was like connecting the sensors to the actual app, because that was a big difficulty. And like the their like software development kit wasn't very helpful in terms of getting that. So I kind of figured out on my own how to connect between the phones and the sensors. But eventually figured it out, and then that was the main struggle this summer. But once I did that, it was fairly easy to go from there.
All right, thank you, Colin. And we will finish up with our last speaker. And so, Sakar, you've got the presentation ready to go?
Yeah, I can share the screen. Yeah.
Yeah, I wasn't able to get it updated in time, so.
Yep, I guess I distracted, but I'll get you the correct introduction here. I need to go back. There we go. So again, Aidan Henley, and on the presidential election 2020, predicting that with multiple logistic regression.
Okay, so I guess we'll just get right into it. So our objective with this project was to use national polling data to create a predictive model to predict the 2020 US presidential election. So the obvious question is, why would you want to predict an election that's already over? You can just go look up the results for yourself. The idea, there's kind of like two goals with this. Once we've created the model, we can go inside it and look at how the model thinks various factors affect voting preference in 2020. And additionally, we can also take the exact approach that we use for the 2020 data and just apply it to 2022 or 2024 to predict the elections then. So next slide. So the data we chose to look at was the Democracy Fund and UCLA Nationscape survey, specifically the 2020 survey data. They surveyed about 6,200 people weekly, and it was conducted over a year from July 2019 to June 2020. We focused on the 2020 data. We wanted to keep it as recent as possible. And new surveys are conducted yearly. So in 2022, 2024, we can use the exact same survey data to get our prediction. And however, the issue with it is it asks hundreds of questions, and we can't use hundreds of questions to train the models. So we had to trim it down to about the 15 most interesting to us. So at the top is Trump-Biden, which is our response variable. It's if the general election is Trump versus Biden, who would you vote for? It's important it's phrased like that because for the majority of the survey data, the Democratic primary hadn't been finished yet. So it had to specify that Biden is the one up against Trump. In addition to that, we have 14 explanatory variables. Those are age, education, employment, police favorability, gender, Hispanic, household income, opinion on Medicare for all, opinion on minimum wage, does the respondent get their news from Facebook, sexual orientation, ethnicity, religion, and state of residence, which includes DC. So first, we had to split our data into a training and a test set, pretty standard procedure. Test set is larger, used to train the model, and the test set we keep off to the side. And once the model is trained, we use that to make our prediction. For the test data set, we used specifically the weeks of April 23rd, May 21st, and June 18th. We wanted them pretty recent, but still kind of spread out. The type of modeling we decided to use was multiple logistic regression for a number of reasons. It takes a number of explanatory variables and it gives a response variable out from that. It does this by assigning a coefficient to each explanatory variable, which indicates how that variable affects the response variable. We can interpret these later, which was a big draw of the multiple logistic regression. It's also important that it's logistic regression because logistic regression focuses specifically on binary response variables. So in our case, we counted a vote for Trump as 1 and a vote for Biden as 0. There's no real significance to it. We just had to choose 1 to be 1 and 1 to be 0. And once we train the model, it'll predict the probability of our binary outcome for each respondent. So For example, if it gives 0.67, that's a 67% chance to vote for Trump. We can use this probability once we have it to predict who will vote for. If they're above 0.5, we give it to Trump. If they're below 0.5, we give it to Biden. So on top of the normal logistic regression, we decided to add a ridge regression penalty. Regression models can often run into issues when there are sort of hidden correlations between the input variables. And so we decided to use ridge regression to sort of mitigate that. What ridge regression does is it shrinks the less influential coefficients and it keeps the important ones about the same value. It helped our accuracy out a lot. And in addition to just a standard prediction, we wanted to have 95% confidence intervals for each state. And so we did this through bootstrapping, which lets us simulate the entire US population from just our data set. We used a specific technique designed for logistic regression models, which we have listed in the appendix. And so here are our results. This is our heat map we generated. The percentages in there are percentage of Trump voters, and just 100 minus that being the percentage of Biden voters. We got 47 of the states correct. The only ones we didn't guess right were Arizona, Georgia, Iowa, and Washington, D.C., which we'll get to later. This is basically the same data, but instead of showing the our concrete prediction, it shows the 95% confidence interval, which are those bars in blue. The model is basically certain that whatever the actual proportion is, it's going to land in there somewhere. And the little X's are what the observed proportions were on election night. They're not all inside the bars, but they're all fairly close, except again for DC, which we'll talk about in a little bit. And so here's just some more statistics on our prediction. For the national popular vote, we actually got within 0.2% of the actual popular vote, which was pretty close considering a study by the AAPOR found that out of presidential polls predicted for the 2020 election, they were off by almost 4% nationally. So we got fairly close. Our electoral vote wasn't quite as close, but 25 is still fairly, only 25 away is still fairly good. It should be noted that we factored third-party candidates out because our model predicts a binary response. So our data doesn't even factor third-party candidates in. And so these are the coefficients I was talking about earlier. So the model sort of gives them in the form of odds ratios, which are a comparison between the odds of one group voting a certain way to the odds of another group voting a certain way. So odds being the probability of success over the probability of failure. So some of the key ratios that we found the most influential or most interesting, the odds of men voting for Trump is about double the odds of women voting for Trump. So as income level increases, the odds of voting Trump slightly increase. And as education level increases, the odds of voting for Trump slightly decrease. The odds of voting for Trump for those who oppose Medicare for all are almost 6 times the odds of those who support, along with minimum wage. That was by far the most influential variable we had. And another interesting thing we saw was that there was no real difference between the odds of someone 18 to 29 and 65 or older voting for Trump, which is a bit of a surprising result, even though 30 to 44 and 45 to 64 age groups were both more likely to vote for Trump than either of those other age brackets. And so there's room for improvement that we could have added had we had a little more time. We probably would have done k-fold cross-validation next, which lets us create multiple test data sets for comparison. It can mitigate the problems of unrepresentative test data. We could have added interaction terms, which let us see how 2 separate variables interact with each other, which our model currently doesn't factor in right now. And we could have tried to apply other machine learning algorithms. I know we were thinking about a decision tree at some point as well. And as valuable as the Nationscape survey data is, we did see some places where the samples weren't super representative of the overall population, like DC. If we looked at the survey data itself for DC, it predicted about 50% of people in DC voting for Trump, which is very, very far from what we saw on election night, which was 5% of the citizens of DC voting for Trump. That was the only place we saw anything that major, so we're not sure what was going on there, but it's something to think about. And yeah, so any questions? Oh yeah, and here's our bootstrap algorithm that we use.
So can you see the question there from, I'll just read it, from Reilly Sollenberger. What is the real world benefit of predicting an election?
Yeah, that's a pretty good question. I mean, predicting the election doesn't exactly change it, but it lets people, specifically people who are working with either candidate, to like see what's going on, see where they need to focus their attention, see like what kind of people they need to try to get to vote for them, where they could improve, what they could do better next time.
We have time for one more question if we have another question. If not, I'd like to thank all of our speakers for a great session, and it was great to hear about all these exciting projects. Thank you.
Thank you. Great work.
Great job, guys.
And so I believe, I guess we just stay. You can go to a different breakout room or stay here. We've got more presentations coming up in this room. And Mark, I believe you are chairing the next session.
Yes, yeah, we'll be getting started in about 8 or 9 minutes. So